In this video, we're going to take a look at a couple more special vectors that are associated with these vector curves. Now, previously we defined the unit tangent vector. So just as a reminder, so let's say we have a curve. This could be flying somewhere in space. So there is the curve. And we have its vector function. The unit tangent vector is a vector, and I'm going to draw it at several points here, where it's tangent to the curve, so it points in essentially the same direction that the curve is going in, and it's tangent, and it has a magnitude of 1. That's why it's a unit vector. So I'm going to try to draw all of these so that they're roughly the same length, right? So, I'll write it in blue. So we have the unit tangent vector, and that notation is big T with the little harpoon on top. And yes, it is a function of T, so we can do that. And what it is, it's you take the tangent vector, which is the derivative of our curve, and then you normalize it. So you divide by its magnitude. So the unit tangent vector, this is how it's defined. It's r prime of t, essentially divided by the magnitude of r prime of t. And of course, this assumes that we're not dividing by 0. So the derivative vector can't be the 0 vector. Right? Okay, so the next special vector that we're going to define is what we're going to call the unit normal vector. And normal is another word that is synonymous with perpendicular. So you have perpendicular, you have orthogonal, you have normal. Those words are all used to convey two things that meet at 90 degrees, right? For lack of a better phrase. So what we want to define now is another unit vector that is orthogonal or perpendicular or normal to the blue vector. So we actually want something like this. Now, the one that we're going to define, right? Because if you think about it, they're basically two vectors that I could draw that are orthogonal or perpendicular to the blue vector, right? I could draw it this way or I could draw it this way. The one that we're going to define, this one in red, is actually going to point towards the inside of the curve. So like wherever it seems like the curve is bending towards, that's the direction that our normal vector will be pointing in. So let me add the other ones. And again, these are all going to be unit vectors. So I'm going to try to make them the same length roughly, and they all are going to be, so the red and the blue are going to be perpendicular, right? So the question is, how do we find this red vector? Well, previously we showed this. We said that if the magnitude of a vector, let's say a vector function, if that magnitude is constant, so if a vector, and again it could be anything, but if that vector function, if the magnitude of that vector function is constant, then we showed that r and r prime, right, the vector function and its derivative must be orthogonal, right? So r orthogonal. Well, think about it. Our unit tangent vector, right? Since it's a unit vector, since it's always the result of a normalization process, then its magnitude is always 1. So in fact, its magnitude is not just any old constant, but it's actually 1, right? All those blue vectors that I've drawn, right? They are unit vectors. So since the magnitude of t, and I'll drop the of t part for now, but since the magnitude of our unit tangent vector is equal to 1, then it follows that t and the derivative of t are orthogonal, right? So there we go. So essentially what we have now is an idea of how to get those vectors in red, right? Simply by differentiating our unit tangent vector. The problem, though, is when you differentiate a unit vector, the derivative isn't necessarily a unit vector. So what we have to do, even though we now know the direction of that is perpendicular to the blue, if we want to call it a unit vector, then we have to normalize it as well, right? So now t prime, right, is not necessarily, it could be, but it doesn't have to be, is not necessarily a unit vector. So we normalize, right, and define. So, and define. And it's often, so the one that we're defining is the one that, like I said, kind of points towards the inside of the curve, right? So it seems like wherever the curve tends to be bending towards, that's where our normal vector will be pointing. And for that reason, it's called, so and define the, it's called the principal or main unit normal vector as, and let me write this one in red since we're defining the vector that I have drawn in red there. And it is, so we use big N for normal again, and it's assumed that it's unit, right? Well, not assumed, but the calculation ensures that it is a unit vector, and we the one that points towards the quote unquote inside of the curve is what we describe as the principal one. So big N, vector N, is defined like this. You take the derivative of the tangent vector and then normalize it. So like this, right? And again, it's assumed, so I'll just say where the magnitude of t prime is not 0, because we can't have a 0 in the denominator, right? So now we have a formula for n, right? So all these vectors, right? If we know the value of t that defines that point on the curve, then all we have to do is plug t into this function, and it will give us our principal unit normal vector, right? So you can see that property that we established earlier. Again, sometimes you get these results and they're like, okay, it's an interesting result, but what do I do with it? Well, here is a direct usage of this particular property. One of our consequences of the derivative of a vector function. All right, so that's our principal unit normal, and so now we have two special functions, vectors associated with our vector functions. Well, what more can we do with it? Well, it turns out there's a third one that we can define. And it is a vector, right? That is, and again, we want it to be another unit vector. It is a unit vector that is going to be orthogonal to both the blue and the red, right? So let me see if I could add something along here. So yeah, it's almost like you'd be creating your own little 3D system. So you have a 90 degree there, And then I know it doesn't look like it, but it in this case it's probably coming out of the board at us, right? Kind of like our x-axis in our our right hand orientation, or maybe something like this. Maybe that would be a better way to do it. And then over here like this. So yeah, these three vectors now, the green vector, right, is a unit vector, and it is orthogonal to the red and the blue. So just the way I've drawn it, and maybe let me fix this one, make it a little bit clearer. Yeah, so it's almost like it would be coming out at us like this, right? It almost looks like what we're defining when we find these, what will be in a second, three special unit vectors associated with a curve. It's almost like we're defining a coordinate system at each point on the curve. That's pretty wild when you think about it. We're defining a three-dimensional coordinate system with these three mutually orthogonal vectors at each point along a curve. Wow. Okay, so let that kind of sink in. Well, the nice thing is it's not too much more work. Well, in principle, right? To come up with this green vector, right? So, the unit vector that is orthogonal to both t and n. So the unit vector that is orthogonal to both our unit tangent and our principal unit normal is called the binormal vector. So it is called, in fact, I'll put the word unit in there, the unit binormal vector, right? And you could probably figure out why we put the prefix bi, right? So this third vector is orthogonal to the previous two vectors. So that's why we use the prefix bi. And found using, now let's think about it. We have two unit vectors, or in general, we have two vectors, and we want to find the direction of a third vector that is orthogonal to those two vectors. That sounds like, right, and correct me if I'm wrong, doesn't that sound like a property of the cross product? Because we know if we take u and v, two non-zero vectors, compute the cross product of those two vectors, then the cross product is going to be orthogonal to the other two. And that's exactly how we find the binormal vector. So I'll use this one, the color green, since I used green on our curve, and it shouldn't be a surprise, but we use uppercase B for binormal, and this is how it's defined. Again, this is also a function of t, and it is the unit tangent vector crossed with the principal unit normal vector, right? So t crossed n. Now, so this is essentially just using the property of the cross product. And the difficulty arises sometimes when we have to compute n, right? Because remember your unit tangent vector, right, is already something that's normalized. It's going to have a square root in the denominator. And if you have to use the quotient rule and the chain rule and a lot of algebra, it could be messy. It turns out there is a formula that now the derivation of the formula that I'm about to give you is really, really long. So I'm going to skip that and just state an alternative way that you can find this unit binormal vector based solely on R. So you don't have to go through T or and N in order to get it, right? So let me state that formula and then we'll do an example. So an alternative formula for computing B, right, is, so I'll again, I guess, yeah, let's write that one in green as well, since it's the same vector, just a different formula. And what you do is you take the derivative of your vector function and you take the second derivative of your vector function and you take the cross product. It turns out that's all you need to do, right, to get the orthogonal direction. But then to make sure that it's unit, we have to normalize this. So we divide by the magnitude of r prime of t crossed with r double prime of t, right? So this way is slightly more direct. I mean, here you have to find the t and the n and then do the cross product. Here you can just find your first and second derivatives of the vector function and then compute the cross product of that, right? That gives you the direction that's orthogonal to t and n, but then you have to normalize it since we want all of these vectors to be unit vectors, all right? Okay, so let's do an example where we're going to start with R and we're going to find T and N, and then we're going to use both of these formulas to compute B, just so that we illustrate the, pretty much everything that can go into questions like this or come up into questions like this. So here's our vector function. It is... And I'll keep it fairly simple, and in general these tend to be pretty simple just because the normalization process can lead to some pretty messy derivatives, right? So these vector functions, their components tend to be relatively simple if you're expected to go through and find both, all these special vectors, the t, the n, and now the b. So for this vector function, find the unit tangent, principal unit normal, and binormal vectors. All right. So let's say we were just asked to find t. All right. That's probably the simplest one. So we take our first derivative. So differentiate r. That gives us 1, 3 cosine of t and negative 3 sine of t, right? And then as soon as I compute this, I'm going to compute its magnitude because we're going to have to normalize this in order to get t. So let's write down the magnitude of r prime. So that's where we square each component. So we have 1 squared plus, now when I square 3 cosine t, I get 9 cosine squared t, plus when I square negative 3 sine t, I'll get 9 sine squared t, and then that's all under my square root. Now, this is something that we're going to end up doing a lot, especially when you see sine and cosines in your components. What we can do under the square root is factor out a 9. So I can have a 9, and then in parentheses, I'll have cosine squared t plus sine squared t, but we know that is equal to 1, right? So that's our Pythagorean identity. So we have 1 plus 9. So the magnitude of this derivative vector is the square root of 10. And this is helpful because the magnitude is a constant, right? So that will make the subsequent derivatives a little bit easier to find. So now we can write down the first of our three special vectors. So the unit tangent vector is you take your derivative, divide it by its magnitude, but in this case, that magnitude is just the square root of 10. So basically divide each of these components by the square root of 10. And here we go. So 1 over root 10, and then 3 over root 10 cosine of t, and then negative 3 over root 10 sine of t. All right, so there we go, 1 out of 3. So we are 33 and a third % complete in this task. Now what about n? So we know, again, the idea is that since this is now a unit vector, it has constant magnitude. In fact, this vector now has a constant magnitude of 1. Well, when I differentiate it, that theorem that we proved, it guaranteed that we're going to end up with a vector that is orthogonal to this, right? So by differentiating a vector with constant magnitude, you're going to get a vector that's orthogonal to it, right? So let's go ahead and find our t prime. Well, what's nice about the first component is that now when I differentiate this constant, I'll get 0. When I differentiate my 3 over root 10 cosine of t, I'll get negative 3 root 10 sine of t. And then when I differentiate negative 3 cosine, or negative 3 over root 10 sine, I'll get a negative 3 over root 10 cosine of t. All right. But I can't say that this is our unit normal vector. It is normal, but I don't know if it has magnitude 1 or not, right? Well, how do I figure that out? Well, I find its magnitude. So again, right beside it, I'm going to compute the magnitude. So we can get the magnitude of t prime. So we'll have 0 squared plus, now when I square negative 3 over root 10, I'm going to get positive 9 over 10. And then I have to square the other factor, sine squared. So I have that plus. And then the same thing here. When I square this, I'll get 9 over 10 cosine squared of t. And once again, we have the same Pythagorean identity. We factor out the 9 over 10. And then I have sine squared t plus cosine squared t all under the square root. Again, what's in the parentheses, the larger pair of parentheses, is equal to 1. So I have the square root of 9/10, which is 3 over root 10. So we can see that, yeah, the derivative of our unit tangent vector is not a unit vector, right? So in fact, because this magnitude is 3 over 10, so what do? We normalize this vector in order to get our n vector. So our principal unit normal vector is, and let me write down the formula, so it's the derivative of your unit tangent vector divided by the magnitude of the unit tangent vector. So in this case, we're dividing by 3. So in fact, let me write it like this. Another way to express this is 1 over the magnitude, which is the 3 root 10, times the vector that we're normalizing, which is the 0, and then negative 3 over root 10 sine of t, negative 3 over root 10 cosine of t. But if I'm taking the reciprocal of 3 over root 10, then it's the same as root 10 over 3. If I just, flip it over, and then when I distribute it to the components of this, our vector, look at what's going to happen. It's like the constants will multiply out to be 1. right? So if we distribute it, the first component is 0. That's pretty clear. But then I have root 10 over 3 times negative 3 over root 10. Yeah, so I end up with a negative 1 sine of t. And then same thing here, a negative 1 cosine of t. Right? And this vector now, if we were to check it, we would see that it is, in fact, a unit vector, and it is orthogonal to this vector. I will leave it to you to check. How would you check? Just do the dot product. If you do the dot product of t and n, and if it comes out to be 0, then you know that they're orthogonal, right? In fact, when I look at it, I can see how it will cancel out, and you will get a dot product of 0. All right, so we're now 66 2/3% complete for this project. We have to find b. How do we find b? Well, b, using the definition with the cross product. Now, these two vectors, again, these are the two vectors that we're going to have to cross. This one and this one. Those aren't too complicated at all. I mean, we can set up our 3x3 determinant, make this my second row, make this my third row, and work through it. Let's see what happens, right, to find b. So the unit binormal vector now is t crossed with n. So since it's a cross product, I'm going to set up my 3x3. In fact, let me do it column by column. That way I know I'll have enough room. So our t is, okay, so let me make this a little bit longer. So t is 1 over root 10, and then we have the 3 root 10 cosine t, and then negative 3 root 10 sine t, and then here's our j, and then there's our k. And then let's now put the components of n in my third row. So 0, negative sine of t, and then negative cosine of t. All right. So let's see what's going to happen. So remember how we compute this. We're going to have, and let me go ahead and set up all the 2x2 determinants that we need. So for the first component, when I block out the first column and the first row, I'm left with this 2x2 determinant. So I have the 3 over root 10 cosine of t minus 3 over root 10 sine of t, and then negative sine of t, negative cosine of t, and then that will be times I. And then I'll have minus, when I block out the middle column, I have 1 over root 10, negative 3 over root 10 sine of t, and then 0, and then negative cosine of t, and then that will be times j, and then plus, finally, blocking out the third column again in your first row, we're left with 1 over root 10, 3 over root 10 cosine of t, 0, and then negative sine of t, and then that's times k, right? All right, so now let's compute the 2x2 determinants. And what do we have left? So we have 3 over root 10 times negative cosine squared. So I'm going to put it as negative 3 over root 10 cosine squared. And then, now when I multiply these two, I'll get a positive number, but then in my determinant formula for the 2x2, there's a subtraction. So again, it'll be minus 3 root 10 sine squared t, and that's all times I, right? And then let's bring down the minus and let's open some parentheses. Now these are going to be a little bit easier because I have a 0 in this position. So I'll do 1 over root 10 times negative cosine t is going to give me negative 1 over root 10 cosine of t. And then I guess you could say it'll be minus 0, right? And then that's times j. And then plus, open parentheses. Again, something very similar. We'll have negative 1 over root 10, but now times the sine of t, and we'll still have minus 0 times k, right? Now remember, we have to get a vector out of this, so don't forget your standard unit vectors, or if you're going to write it in the angled bracket form. But what happens is if I factor out a negative 3 over root 10, look at what I have left. My Pythagorean identity yet again. This is like the third time we're using this identity. And then I. Now let's see. So just distribute the negative. So this becomes a plus 1 over root 10 cosine of tj. And then there's a negative 1 over root 10 sine of tk, right? And then, of course, we're going to simplify this. So I'll write the final answer using the angled bracket so that it looks like all the other ones. So I'll just say, therefore, our binormal or unit binormal vector is given by this first component is negative 3 over root 10. The middle component is 1 over root 10 cosine of t. And then the third component is negative 1 over root 10 sine of t. And there we go, right? So that's our binormal vector. So all three vectors, right? The t, the n, and the b, if you take any pair of them and compute the dot product, you will get 0. So I'll just make a note and then that will wrap up this video. So note T, N, and B are what we call mutually orthogonal. Just like your I, J, and K, right? Those standard unit vectors are mutually orthogonal. So are your unit tangent, your principal unit normal, and your binormal vectors, right? Taking any two of these and doing the dot product will produce 0. So I'll leave it for you to check. It's a nice little exercise to, again, practice your dot product and illustrate that really important property. And I'll see you in the next video.